In the last class, we started discussion on the MOS junction. We shall continue this discussion in this particular lecture. You would recall that we have set ourselves the goal of explaining the CV characteristics shown on this slide. Now, what we achieved in the last class is that for an ideal MOS capacitor, we have explained the accumulation, depletion and inversion regimes of operation. We can show these various regimes of operation on a simple diagram. So let us draw a line indicating the various conditions in the semiconductor as far as the electron concentration at the interface is concerned. So this shows Ns on a log scale. Now, what is Ns? If these are the hole and electron concentrations for any voltage, this quantity is Ns and this quantity is Ps, and this bulk concentration of electrons, this we will denote as N naught. Now, suppose this is N naught, this is Ni and this is P naught. Okay, so P naught is this bulk concentration of holes. We can identify the regimes of operation in terms of these concentrations. When your N is less than N naught, that is this regime, you have accumulation. When N starts becoming more than N naught, or correspondingly the whole concentration starts becoming less than P naught. So here you have depletion. Now this depletion continues until your Ns becomes equal to P naught. Now in this region you can separate and you can identify a weak inversion region when your Ns is more than Ni but less than P naught. So this is weak inversion. Recall what we said about inversion. Just as depletion implies removal of majority carriers, inversion is nothing but pile up of minority carriers. So that they dominate the bulk majority carriers. So whatever are the majority carriers in the bulk, they are dominated by the minority carriers at the interface. Okay, so at the interface, the minority carriers in the bulk are really the majority carriers, okay, because they are dominating. So weak inversion, and beyond Ns equal to P naught, here you have strong inversion. Now in our first course what we said is that we will call this region as the inversion region. Whenever we use the word inversion, it would imply strong inversion. The treatment of weak inversion is more complex, so that is taken up in advanced courses on semiconductor devices. Now what is it that distinguishes strong inversion from weak inversion? The pileup of the electron charge at the interface as shown in this diagram, that is this area, starts becoming significant in the strong inversion region. Now we can translate this diagram that you are able to see also to the voltage axis. So for example, in terms of voltage, if you show so this is V, that is a gate voltage, then this point when Ns becomes equal to P naught is said to be the threshold point, and this voltage is called the threshold voltage. So this is threshold voltage. On the other hand, this point where the surface concentration of electrons is same as the bulk concentration, or when the charge conditions in the device are 0, is normally referred to as the flat band voltage. So this translates to this point in terms of the voltage conditions in the device translating to terminal voltage, and this translates to the threshold voltage point. Let us understand why this point is called the flat band point. Okay, to understand this, we need to draw the energy band diagram for that condition. So this condition is also the condition V equal to 0 for an ideal capacitor. So VFB is equal to 0 for ideal capacitor. Now what is this flat band? What is the meaning of this flat band? So if I draw the energy band diagram in this semiconductor for V equal to 0, which is a flat band for ideal capacitor, you will find that the conduction band edge and valence band edge, both of these edges are flat, they are horizontal. That is because there is no variation in the hole or electron concentration as a function of x for V equal to 0. So recall that the hole concentration is flat and electron concentration is flat for V equal to 0. So this hole and electron concentration conditions, flat hole and electron concentration conditions, translate to flatness of the conduction and valence band edges, and therefore this condition is called the flat band condition. Please note that we are considering a uniformly doped substrate. If the substrate is non-uniformly doped, then even when voltage is 0, the doping will result in a non-uniform hole concentration, electron concentration, and then the bands won't be flat. So for our case, we understand why the voltage equal to 0 condition is referred to as the flat band condition. So accumulation implies voltage less than VFB. From VFB to VT, this is the depletion region, and for voltage, gate voltage beyond VT, you have the inversion region. Now we need to find out what is this threshold voltage. We already know that the flat band voltage for an ideal capacitor is 0. Now for this purpose, we need to translate our hole and electron distributions in the semiconductor to charge and electric field conditions. So let us see how we can do that. Now for the threshold condition, the hole concentration is shown here, okay, as 4, and the electron concentration also has been shown. It turns out that this electron concentration, that is the area under the electron distribution, this is really small compared to the charge because of depletion of holes. So we can neglect this charge under threshold voltage conditions, that is at threshold voltage condition. That being the case, we can draw the charge and electric field conditions as follows. So this is our hole concentration. On a linear scale. Now we draw the space charge. Since the charge is negative, we draw it on the negative side. So that is a space charge, where this value here is minus q times Na. Approximately, we know from our p-n junction theory that in depletion layer the space charge concentration is minus q times the ionized impurity concentration. We are assuming complete ionization. Now we will assume the depletion approximation, that is, we will assume that this region has an abrupt ending for simplicity of analysis. So based on this, now we can sketch the electric field. The electric field is on the positive axis because electric field is positive from left to right. This charge is negative. Now since this is constant, this charge is, space charge is constant here by Gauss's law, we will get a straight line for the electric field up to the interface. Now what happens in the oxide? You know that when you move from one region to another region of different dielectric constant, then the electric fields on the two sides of the boundary are related by the formula epsilon 1 E1 is equal to epsilon 2 E2. So these are the two electric fields. This is E1, this is E2. The dielectric constants are epsilon 1, epsilon 2. Okay. Now, using this particular relation, if you call this as the surface electric field in semiconductor, that is, we give this the symbol ES here. Now, in terms of this, we can draw the electric field in the oxide. So in the oxide layer, the electric field would be constant because there is no space charge, and this electric field would be related to this electric field by this formula. So we can substitute the dielectric constants here, and then we will find this is epsilon ox. So this is E ox, so therefore this is epsilon ox, and here it is epsilon silicon, and this is Es. So from here we have E ox is equal to Es into epsilon silicon by epsilon ox. Epsilon silicon is 12 and epsilon ox is 4. So this is equal to 3 times Es. So therefore you take 3 times this, and that is your E ox, field in the oxide. Now what happens in the metal or gate? Obviously you have the opposite charge. So here you have the charge shown by delta function on the positive side, because you have a positive charge. So the electric field will abruptly drop to 0 in a small distance. Okay, that field is not of interest because it falls abruptly in the metal. Now this area under the electric field distribution is the applied voltage, and that is the threshold voltage. So to know the threshold voltage, we need to know this area. Now let us identify the components of the applied voltage across oxide and across semiconductor on the electric field versus X diagram. So here this area is the voltage drop across the oxide, that we will indicate as psi ox. On the other hand, this area is the voltage drop across semiconductor, and this we will denote psi s. So let us see in terms of our capacitor, what are these components. Now you are applying a voltage here, and this voltage is falling across the oxide and across the semiconductor. This is the applied voltage V. So in general you have V equal to psi ox plus psi s. Now we need to identify psi ox and psi s. We need to get the values. Now it is interesting to note that you can get psi s from the hole and electron concentrations versus distance diagram at threshold. So at threshold your concentrations of electrons and holes are as follows. So Ns is equal to P naught. That is a point here. This is hole concentration and this is electron concentration at threshold. You can use Boltzmann relation because this semiconductor is under equilibrium. So Boltzmann relation gives you the potential drop in this region if there is a variation as shown here. Now this value here is N naught and that is P naught. So this potential drop here, which we call psi s, that is the potential drop in the semiconductor, can be written as Vt into ln of the concentration here that is Ns by concentration in the bulk, that is N naught, which is nothing but Vt ln P naught by N naught. This is the Boltzmann relation. Now we can simplify this equation because we know we can write N naught in terms of P naught. So this is nothing but Vt into ln of P naught by Ni square by P naught, because P naught N naught is Ni square. So which will then simplify to 2 times Vt into ln of P naught by Ni. So that is your psi s. So psi s is equal to 2 times Vt ln P naught by Ni. Now we know what is P naught. P naught is approximately the doping of the substrate, that is P naught is approximately equal to Na. So therefore we have the relation psi s is approximately 2 times Vt ln Na by Ni. In other words, we know the value of psi s at threshold, okay, in terms of the substrate doping. So this is psi s at threshold. So in other words, we have identified this area here. Please note that the psi s will vary with voltage. We are talking about the conditions right at threshold. Now once we know this, we know this area also, because we know this Eox is 3 times Es because of the dielectric constants of silicon being 12 and oxide being 4. Therefore now we can write an equation for threshold as follows. So threshold voltage is equal to Psiox plus 2 times Vt ln Na by Ni, where Psiox is Eox into Tox or T naught. We are using the symbol T naught for the oxide thickness, which in turn is equal to 3 times Es into T naught, because Eox is 3 times Es. And for Es you have a relation this area is 2 times Vt ln Na by Ni, but this area we can write in terms of Es and doping level itself, okay, using our analysis that we did for p-n junction. So for Es your relation is half of Es into the depletion width xd. The depletion width xd is this. So this is 2 Vt ln Na by Ni. Now this xd we can again write in terms of the charge. So this xd is nothing but the depletion charge which we denote as Q suffix d. We are putting a modulus because the depletion charge is negative. What is the depletion charge? Let us look at this diagram. This is the depletion charge. So Q suffix D. Of course, at threshold this also happens to be the charge in the semiconductor Qs, but that is a different issue. So now XD is QD divided by the doping multiplied by Q, and this QD and ES are related by Gauss's law, that is this ES and this QD. So what is the relation? The relation is QD is equal to epsilon S into ES, but ES is positive and the charge is negative. So QD is minus epsilon S ES, but modulus of QD is epsilon S ES. So here in this formula you can write this QD by QNA as epsilon S ES upon QNA, so that now you can replace XD in terms of epsilon S and you have the relation half of ES square upon QNA into epsilon S. This is the left hand side. So this is equal to 2 Vt ln Na by Ni. Now let us indicate this particular voltage which is coming often with a symbol, so that we do not have to write this whole term. Let us call this voltage as phi t, that is the surface potential at threshold. Note that the potential drop in the semiconductor, that is psi s, that is this here, is also referred to as surface potential, because this psi s is the potential of this point with respect to the bulk, and this is the surface. So that is why it is called surface potential. We are assuming that the bulk potential is 0 in the semiconductor reference. So from here we can derive the following formula for ES. ES is equal to 2Q Na phi t by epsilon s with a square root. Now we can substitute this value of ES here and therefore get this psiox, and we will get the expression for threshold as Vt is equal to 3 times T naught into 2Q Na phi t upon epsilon s plus phi t. Now this 3 is nothing but the ratio of the dielectric constants of semiconductor and oxide. So we can simplify by writing this 3 as epsilon s by epsilon ox, and then we can cancel these terms and shift this epsilon s to the numerator, and now epsilon ox by T naught we know is the so called oxide capacitance C naught. So we can write this formula as square root 2qNA phi t epsilon s upon C naught plus phi t, where phi t is given by this 2 Vt ln Na by Ni. So now this is the equation. Let us write it completely. So this is the equation for threshold voltage of an ideal MOS capacitor. We have on the right hand side all the material parameters. So basically you see it depends on the doping level Na, the temperature T because that decides Ni and Vt, and the oxide thickness which decides the C naught. Of course you also have the dielectric constants coming in there. Now in this form you can identify the particular term, the first term on the right hand side, that is this term, as follows. Since this is the dimension of volts, the numerator is charge per unit area, because charge per unit area divided by capacitance per unit area will give you voltage. Now what is the charge that we are talking about here? This charge is nothing but this particular charge, the depletion charge here, okay. So this is identified as QD at inversion with a modulus because the charge is negative. Now this is again a charge per unit area. We need to emphasize that the area we are talking about is perpendicular to the board, okay. So that is, the area is perpendicular to this. Now what does this QD by C naught term indicate? It is like the voltage across the insulator of a parallel plate capacitor having charge Q. So that is how this formula is very easy to remember, okay. In this formula, this is the potential drop in the oxide which is given by the parallel plate capacitor formula, charge on the electrode of the oxide, that is a semiconductor, divided by the capacitance, and this is the voltage drop in silicon. So voltage drop in silicon plus the voltage drop in oxide at threshold, you sum up and then you get the threshold voltage. So now it is useful to get some feel for what kind of values we get for the threshold voltage. So we will do a solved example. The solved example is, calculate the threshold voltage of an ideal MOS capacitor having the following parameters: P substrate doping level of 1.45 into 10 power 16 per centimeter cube and an oxide thickness of 0.2 micrometer. The temperature is 300 K. Basically these are the parameters corresponding to the experimental CV curves that we showed and which we are going to explain. So let us start using this formula. If you substitute the various parameters, what kind of values we get for the two terms on the right hand side. Let us calculate phi t first. Phi t at 300 K is 2 into 0.026 volts into logarithm of 1.45 into 10 power 16 divided by 1.5 into 10 power 10. Now use your calculators. You find that this is approximately 10 power 6. So when you take log of 10 power 6, 6 will come out and you will have ln 10. So that 6 gets multiplied by 2, you have 12. So 12 times 0.026 into ln 10. It turns out that this quantity will be about 0.72 volts. So this phi t value is somewhat like the value of the built-in voltage of a p-n junction, okay, about 0.7. Now the next quantity to calculate is this C naught, which is the capacitance of the oxide per unit area. So C naught is epsilon ox upon T naught, which is 4 into 8.85 into 10 power minus 14 farad per centimeter square, divided by T naught is 0.2 microns. So into 10 power minus 4 centimeters. I am sorry, this is farad per centimeter and divided by centimeter. So you see the capacitance is farad per centimeter square. Now this value, if you see, it will be of the order of nanofarads, okay, because this 10 power minus 4 goes up, it becomes 10 power minus 10, but then you have 0.2 here, so multiply numerator and denominator by 10, this will become 2, and here you will have 10 power minus 9. So this value is 17.7 nanofarad per centimeter square. Now it is useful to remember this value of C naught, typical value of C naught, like we remember the typical value of phi t, which is about 0.7. Now please note that phi t is logarithmically dependent on the doping level here. So even if the doping level changes, the value of phi t does not change very significantly. You will find that it will remain between 0.6 and 0.8 volts, around that. So 0.7 is a good value to remember. Similarly, for C naught we find that for 0.2 micron thickness oxide, the capacitance is 17.7 nanofarad per centimeter square. It is useful to remember the value for 0.1 micrometer, okay, because 0.2 micrometer is not so easy to remember. Relatively it is easier to remember the 0.1 micrometer thickness, which is same as 1000 angstroms, okay, in terms of angstroms. Whenever you are handling small geometries, you must be very comfortable with dimensions of the order of angstroms and microns, and you must be able to convert one from the other. So 0.1 micron oxide thickness is equal to 1000 angstroms. So for this 1000 angstrom oxide thickness, your C naught would be double the value that you obtained for 0.2 microns, okay, because the capacitance is inversely proportional to the oxide thickness. So for this, C naught is approximately 35.5 nanofarad per centimeter square. So one remembers this value. For T naught equal to 0.1 microns or 1000 angstroms, this is the capacitance. So in practice, whenever you come across any other oxide thickness, you can always quickly calculate the capacitance of that particular MOS capacitor by simply scaling by the oxide thickness in appropriate manner, starting with this value. Next we need to calculate the numerator of this equation. So now we can write Vt is equal to, or let us just calculate this term, square root 2q Na epsilon s into phi t upon C naught. So this will be equal to square root 2 into q is 1.6 into 10 power minus 19. So we always collect all powers of 10 together, and we also write the units here, so coulomb. Then doping level, that is 1.45 into 10 power 16. So that we put here, and this is per centimeter cube. Then comes epsilon s. You recall from the calculations done for p-n junction that approximately we can assume the epsilon s to be 10 power minus 12 farad per centimeter for silicon. Basically this value 10 power minus 12 for epsilon s is given by 12 into 8.85 10 power minus 14, because dielectric constant of silicon is 12, and then you have to multiply by phi t, that is 0.72. So 0.72. So we will shift this to the right a little bit, into 10 power this, that is volts. Now this divided by C naught is 17.7 into 10 power minus 9. So this is farad per centimeter square. So you have centimeter square in the numerator and farad in the denominator. Now let us first check the units here. So this is coulomb, and farad into volt is also coulomb. So farad into volt is coulomb, and now coulomb square and centimeter power 4 in the denominator. So this centimeter power 4 in the denominator becomes centimeter square when it comes out of the square root, and this becomes coulomb. So this is the unit. So coulomb by farad, that is nothing but volts. So dimensionally this equation is correct. Now we need to evaluate it numerically. So here you will find you have powers of 16 minus 12, that is 4, minus 19 plus 4 is 10 power minus 15. So now you can make it 10 power minus 16 and multiply this quantity on this side by 10, so that what you get out from the square root is 10 power minus 8. Now bottom is 1.77 in 10 power minus 8. So 10 power minus 8, 10 power minus 8 will cancel. So you will get this of the order of volts. It turns out that this value is equal to 3.26 volts. So now you sum up 3.26 volts and 0.72 volts, and you get Vt is equal to 3.26 plus 0.72, that is 3.98 volts, that is about 4 volts. Okay. So you find that 4 volts, about 4 volts is the threshold voltage, that is the voltage you must apply to the MOS capacitor, that is this voltage, in order to achieve threshold voltage conditions, okay, in the semiconductor. Out of this approximate value of 4 volts, please note that only about 0.7 is falling in the semiconductor, that is this value here, phi t is the psi s, potential drop in the semiconductor, and this is potential drop in the oxide. So you find that most of the applied voltage falls across the oxide and a very small value falls across the semiconductor. Okay, this is something important that we must gather from here. Now let us proceed further and see what happens beyond threshold, because in fact from the point of view of operation of a MOSFET, we will find that it is a regime beyond threshold that is of significant interest. So let us plot the concentrations in the p-type region, p-type substrate, for voltages beyond threshold. So V greater than Vt. Supposing you vary this voltage, what is going to happen? So first start from the threshold voltage point. This is P naught, this is N naught. So this is the whole concentration, this is the electron concentration at threshold. Beyond threshold, what happens is this concentration rises even beyond this P naught value. And this will obviously fall. Now this point is the so-called intrinsic point, okay, because here the hole and electron concentrations are equal and therefore they will be equal to Ni. You will recall from the p-n junction depletion region analysis that even there you had an intrinsic point. Now coming back to the concentrations of, this is electrons and these are holes, you find that Ns is now more than P naught. Now what is interesting to note is that you will find that this depletion edge, this is the edge of the depletion layer, will not change very significantly beyond threshold. This is the important point that we must understand, that the depletion region almost ceases to expand beyond the threshold voltage point. Let us see why. Let us plot this same concentrations on the linear scale. So this is the whole concentration, and this is the electron concentration at threshold. Let us reduce this a little bit. So at threshold, this is what it is, the electron concentration, but beyond threshold this is somewhere here, the electron concentration is like this. This thing when you plot on a linear scale, please note that this is on a log scale, whereas this is on a linear scale. To understand why the depletion region does not expand significantly beyond threshold, you must plot this concentration on the linear scale. And there you find that even a small change here on the log scale in the electron concentration means a large change in the linear scale. This is almost a factor of 10. In fact, we have not shown a factor of 10 increase here. If you really want to show a factor of 10 increase, this concentration should have been shown somewhere here or even beyond. So we are not able to show it to scale. The point is that now if you see this area under this curve, this is going to rise rapidly beyond threshold. Therefore, whenever you apply extra voltage, you need extra charge in the semiconductor. Beyond threshold, what is happening is that extra charge is coming from these electrons. The extra charge comes more easily from the electrons rather than by depleting the holes and exposing the negatively charged acceptor impurities. So until the capacitor reaches the threshold, when you increase the voltage, the extra negative charge required in the semiconductor comes from the ionized impurities by expanding the depletion layer. But once you reach the threshold and go beyond this, whenever you increase the voltage beyond threshold, the extra negative charge required in the semiconductor comes from the mobile electrons which are very close to the surface. And since this mobile concentration now can increase very rapidly, there is no need to expand the depletion layer to provide for this negative charge. Now these aspects can be shown nicely on a graph. In fact, one can do numerical calculation of this situation, the analysis of this to find out this particular charge under this area is not a straightforward analysis, it requires some intense numerical calculations because you have to solve a number of complicated equations. But we can sketch the graph qualitatively to show what is happening here. So for that purpose we will translate this diagram onto space charge versus distance diagram. So if you translate this diagram to space charge versus x, this is how it looks. At threshold, this is your space charge, so rho versus x. And you are not able to show any electron charge here, okay. So this is that electron charge, very small at threshold, but beyond threshold there is a very slight increase here, but here the increase is very, very high. Let us show it with a slightly different color and different line. So the dashed line shows beyond threshold. So here, for example, this is, supposing call this 4 was our threshold voltage. If you recall, curve number 4 was the threshold voltage, so let us call this curve number 5. You should connect this diagram to the diagram we had drawn for carrier concentrations for voltage conditions below threshold. Then you will understand why this is 4 and this is 5. So here this white is 4 and this is 5. So 4 corresponds to V equal to Vt, 5 corresponds to V greater than Vt. So this is the charge that we are talking about. So now you no more have to increase this area under this rectangle to get the charge. Extra charge beyond threshold comes from increase in this negative charge because of electrons. What we will do is we will call this area under the electrons or the electron charge as the inversion charge and denote it by the symbol Qi. Now the charge of electrons is negative, so we will put a modulus here because this area is positive. Now similarly here we will show the space charge because of electrons by a separate delta function here. This is like a delta function, that is, it is showing the electrons as a sheet of charge. So this is Qi. Please note that the space charge is on the negative axis and this area is the depletion charge. Now we sketch Qi and Qd as a function of voltage. As I have said earlier, the calculation for Qi and Qd for V greater than Vt will have to be done numerically, okay. So we are only presenting the results here, based on which we can make a very simple approximation and we can get the charge conditions and we can calculate them. So as a function of V, supposing this is the threshold voltage point and this is the origin or flat band voltage, then your depletion charge goes on increasing like this and almost saturates beyond this threshold voltage. So there is a small increase, okay, but the rate of increase is very, very small beyond this. On the other hand, so this is Qd. If you sketch this Qi as a function of voltage, you will get it as follows. The Qi is very, very small up to threshold and beyond threshold it starts increasing rapidly. So this is Qi. This is the threshold voltage point. So this is the depletion region, and beyond this you have the inversion region. Now we can complete the picture and show the accumulation charge. On the other side, when your voltage is negative, you have accumulation charge. Recall that the relation between accumulation charge and voltage is a straight line. So, and that charge is positive. So this is Q accumulation. Suffix A stands for accumulation. The silicon charge is given by sum of Qd and Qi, because this total thing is the silicon charge. So if you want to sketch the silicon charge, that would look something like this, that we will show by dotted line. So this dotted line is Qs. Here of course the Qs and Qa are the same. Here this Qs is obtained by summing up these two. So beyond threshold it is almost Qi, and below threshold it is almost Qd. So that is the charge condition. Now this explains why or how the depletion region stops expanding beyond threshold, because with increase in voltage the extra charge in semiconductor comes from the mobile electrons and you are getting an inversion layer. Now what we want to do is to derive expressions for Qi and Qd as a function of voltage. We already have an expression for Qa as a function of voltage. So when you have the expressions for Qd and Qi versus voltage, we have the complete Qv characteristics. So what we have drawn here is actually the Qv characteristics that we said we wanted to derive for the MOS capacitor. So this is the charge in silicon versus the voltage. In the next class we will derive the equations for Qd and Qi as a function of voltage. Now here, to complete the explanation, let us see what happens to the potential drop in silicon, because we said the applied voltage drops across silicon and oxide. At threshold we have seen that psi s is equal to phi t, that is about 0.7 volts. Now what happens beyond threshold? Since the depletion charge is almost saturating, or the depletion layer is almost saturating, what we find is that the surface potential or the potential drop in silicon psi s also almost saturates at the value corresponding to the threshold voltage. So if you sketch psi s as a function of voltage, you will find the variation to be something like this. For V equal to 0, psi s is 0. At threshold it is phi t. Beyond threshold it almost saturates at phi t. There is a small increase, but that increase is very, very small. So therefore in inversion we can assume no matter what the voltage is, so long as it is beyond threshold, the surface potential is approximately equal to phi t. The remaining discussion will be taken up in the next class.